All right, so we will start with a quick update here. Here's where we've been, 1 through equilibrium right there. Just finished, or working on finishing that up right now as you take that take-home test. And as you can see, we're going to be doing acids and bases and then applications of thermodynamics. Now, the good news is we have an introduction certainly to both of those, and we're just going to be expanding on them and actually incorporating some equilibrium concepts in them. So these last 2 units just kind of join everything together, and it's a great review of everything we've done, including the chemical reactions. And so let's jump into acids and bases, and we're going to start off with 8.1 and 8.2. So let's go ahead and see what new stuff we got here and take good notes in those packets again. A lot of the introduction will be some review, so just keep that in mind as we move forward here. Here's what we got. The first thing is the auto-ionization of water. Is what we're going to be starting with. Two water molecules can actually undergo this process, making a hydronium ion, where a water picks up a hydrogen, and a hydroxide ion, where a water molecule loses a hydrogen. All right, and these numbers are known in water at 25 degrees Celsius. The concentration, if you could please add molarity signs after these concentrations in your notes. They are missing on this slide. So 1.07 times 10 to the minus 7th molar, and an equal concentration of hydroxide ions. So that means if you were going to do the equilibrium constant of this, and of course the liquids would be left out, Kw equals the concentration of that times the concentration of that, which is 1 times 10 to the minus 14th, always at 25 degrees Celsius. So we know the concentration, we know the pH essentially of water, and this is going to be based on the pH scale. You can think of 7, pretty important number in pH, 14-point scale, not a coincidence, because those numbers are going to become meaningful. All right, so this Kw value, yet another type of equilibrium constant, is going to be the same, and I remember an exam where this was one of the first questions where they jumped in, and then they had you had to know these in order to figure out the hydroxide ion concentration. You had to know these too. So this is definitely something that you're going to have to kind of memorize. So the types of problems you'll see, if the concentration of OH is found to be 1.4 times 10 to the minus 11th, and you want to find out the concentration of H3O plus, all you got to do is plug in the unknowns. Here they rearranged it a little bit. You know Kw, so divide that by the hydroxide ion concentration. Watch your sig figs, and you'll get 7.1 times 10 to the minus 4th molar. All right. So you can see that there's a general equation that they use for acid, because it's always going to have that hydrogen in there, and when that reacts with water, you can make the hydronium ion concentration, or you can leave the water out. You know, it can be assumed because it's an aqueous solution, and just have the H plus and A minus ions. Okay, so that's sort of interchangeable to use either a hydrogen as H plus or hydronium H3O plus in an aqueous medium. They're definitely going to be part of it'll always exist in that form, but certainly okay to use H plus as well. Here's the next one we get into is pH. Definitely something that you've heard of before. We haven't worked on it a lot in chemistry, unless you had organic last year, derived from the French puissance d'hydrogen, meaning the power of hydrogen. So what does that mean? Well, a solution with H3O plus concentration of 10 to the minus fourth has a pH of 4. So what are we doing mathematically when we do that? Well, let's look at a couple of example problems, see if we can figure this out. All right, so if you want to find the pH of pure water, the first thing you need to do is find the concentration of H plus, which you just know is 1 times 10 to the minus 7th. So the pH is 7. So we are using a mathematical tool to figure that out called the logarithm. So log base 10 to the 7th, and you can see it's going to be the negative log of that number. So let's go ahead and do a problem where the numbers aren't quite as clean and easy to predict. So if you have a pH of 5.63, what's the hydrogen ion concentration? So here's how we're going to do this. Since it is log base 10, you're going to go 10 to the negative pH, or just 10 raised to the negative 5.63. That's how we're going to figure out that concentration. So you just 10 caret key, and it'll crunch those numbers for you. And some of you are like, oh, they messed up the sig figs on this problem, when in fact they did not. So here's a little trick for you, and this is going to be repeated a little bit later. But pH for sig figs, think the P instead of puissance or power, we will think of it as being place value. So if you want to know how many sig figs 5.63 has as a pH, the answer is 2. These are the ones that are significant, is the place value. And it has to do with the math of logarithms, but that's 2 sig figs. So your answer, that's why they rounded that to 2.3 times 10 to the minus 6. And you notice this power of 10 will always be really close to that concentration right there. Okay? Now, so this gets us into, finally getting down and say, well, what are we really doing here? Well, it's pH equals the negative log base 10 of the hydrogen ion concentration, or, of course, interchangeably the hydronium ion concentration. So, for pure water, it's pH equals the negative of a negative 7, which, of course, pH would be 7.0. All right? The scale for most things that we deal with the human body and living organisms fall within this 14-point scale. Low pHs having a very high concentration. This is a very mild acid solution. You can go off the chart. We're going to see examples of that. You can go above 14. You can go below 1 and even have negative pH values. But this just gives you an idea, some general household objects and what their pH values are. Some of the things that we're eating are acids and bases. Broccoli is a good example up here, one that has a strong base, that bitter taste to it. This, of course, is review, which some of you showed on the last exam that you knew very well. continue to commit these to memory. You could see this on an upcoming quiz again. What are the big six or the great eight for strong bases as well? Okay, so you just want to be able to recognize those acids. What we're going to do right now is find the pH of a 2.5 molar hydrochloric acid solution. And since it's a strong acid, we're going to assume 100% ionization. In other words, of this 2.5 molar, all of them will turn into H plus ions. So then the equation becomes negative log base 10 2.5. So make sure that you figure out how to plug that into your calculator. If you do that in the wrong area, you're going to get in the wrong order. Excuse me. You will get an error message. So just make sure that you are able to do this. And this is that example I was talking about. Look at that. It's off the chart. It's a negative 0.40, which, of course, this is an awful strong acid solution. It would be very dangerous to any living organism. So it doesn't really fit within that comfortable pH scale. So it's off the scale with a negative 0.40. To find the pH of 0.05 molar, did we talk about sig figs on this guy? Yeah. So this is, I forgot to remind you of that this is 2 sig figs as a concentration, which means 2 places to the right. pH is place value. So to figure out the 2 sig figs, you go 2 places to the right. Sorry, I forgot to mention that. All right. So, here you have the pH of 0.05 molar H2SO4 solution. So that's 1 sig fig as a concentration, and we're looking for the pH. So when you do that, it'll have 1 place to the right. So you punch that 0.05, take the logarithm, drop that negative sign off, that you'll get, and 1.3 will be the pH, because the 1 sig fig, 1 place to the right. Okay? I think we're going to go ahead and start the next video with this problem, because it's a little more involved and might run out of time. So go to video number 2.